And so we're going to start off with question number 2, right? So question number 2, we're looking for this partial pressure of carbon dioxide. And so it gives us this composition of dry air at sea level. And so why do we care that it's dry air? Why is that an important part?
I want to say it has something to do with what's in the air molecules, I guess.
It does. So it does give us a clue about what's in the air, or more importantly, what's not in the air, right?
Okay.
So when it says dry air, what's going to be missing from that air?
Water.
Water, right? And so with atmospheric chemistry, water is a big deal because water concentration really varies based on where you are, right? If you're in like a deserty region, not much water vapor in the air. But if you live in the tropics, your percentage can really drive up. And so a lot of times what we'll be working with is dry air because there's so much water variation. And so a lot of times we'll be just doing it in something that's dry. And so that's why they're telling us that part. So we don't have to worry about the water vapor.
Okay.
Okay. So from here, it's asking us to calculate partial pressure. And so we want to remember that partial pressure is equal to what for our carbon dioxide?
Partial pressure is equal to concentration.
So concentration is part of it. It's this idea that your total pressure, right, for the entire atmosphere is made up of all of their parts. Right?
Oh.
So if we add up the pressure from our nitrogen and the pressure from our oxygen and pressure from the argon and on and on and on, it will equal that total pressure. So our total pressure right now is at 751 millimeters of mercury. And so in the way that concentration kind of plays a role in that, it's more like that percentage that the carbon dioxide is making up is going to be related to our pressure. Right? So we have PV is equal to nRT. And so we want to go ahead and attach our volumes to our pressures. So if all of these gases are at the same pressure, R, and temperature, we kind of can tell that our volume of our CO2 should be related to its pressure of its CO2. So we know that for our CO2, 0.033% of the entire atmosphere is the carbon dioxide. And that would be out of 100%. And so we can kind of set that up as a comparison with our total pressure. So you can kind of imagine that it's 751 millimeters of mercury is equal to that 100%. And so we're trying to look at that's not going to work out. The pressure of that CO2 and how it's related to 0.033%. Right? So there's like a correlation there. In a lot of ways, what we've done is we're doing that combined gas law. Because our temperatures and our total number of moles would be the same, then we can really look at the relationship of their volumes. So if we take that 751, we multiply it by 0.033% divided by 100%, we'll be able to figure out what pressure that is of our CO2. Now, in the question, it does ask us that we do this in ATM. So I'm going to give you a moment to think about what you need to do to turn that into your ATMs. When you get it, go ahead and share out in your chat what your answer is going to be. We can do a comparison, see how we're doing. Yeah. So we want to take this, we want to try to turn this into ATM of our CO2. And when you get that, put that into the chat. That's right, that once you guys have it in your millimeters of mercury, you need to divide it by your 760, right? That's how we're going to get into your ATMs. So think about what our value should be. Because right now, once we did this equation, we're coming out with 0.24783 millimeters of mercury. So how many ATM is that? Or what is that value in ATM might be a better way to phrase that. If you're worried about sharing it with everyone, you can just send it to me. I'll still see it, and we can do that as well. And did anyone else get that same answer?
That's what I got.
That is. And you guys are right, that when we're looking at this one, our ATM should be right around that 3.3. So for us right now, we're limited by the 2 sig figs of the CO2. So we're going to get that value. So very good. Well done. Now we're going to try something. I'm going to give you guys a poll. We'll see how we feel about this, and then we can see if we're ready to move on. So you can click on how you feel. And then we'll get question number, I lost my page. I think it's question number 4 set up for this one. 6. We're looking at question number 6 next. If you're not feeling really confident about this and you want to ask some questions, you can do that as well. So that way we can change all those to smiley faces. So what I would recommend when you look at question number 2, is just remember that your relationship for gases is related to how much material you have there. And so if everything's at the same temperature and the same pressure, then there's a direct correlation there between their volumes, their moles. Same thing that if we can hold everything else the same, if they're all in the same container, then we can always take that overall pressure and we can break it down based on what fractions we have. So when we have this composition by volume, that's directly related to the number of moles, and the number of moles is directly related to your pressure. And so we can use that to kind of go back and forth between those. And so we'll look at question number 6 now. And so that's too many things. So for question number 6, it's asking us to calculate the energy difference between 2 levels involved in this emission process. And it's telling us that we're emitting a photon that has a wavelength of 558 nanometers. Now, whenever it's talking about energy of a photon, there should be an equation that we immediately start to think of, right? Does anyone have that equation?
E equals HV.
E equals HV, right? And so we're going to get that from our periodic table or from your equation sheet. It's right in there next to your atomic structure. Now, we can't just use E equals HV by itself because that's giving us the frequency. So we have to remember that our frequency is tied to our wavelength, and we'll have to combine those two equations. But do we need any other information like your energy levels or anything like that in order to find, to answer this question? So in this case, we don't need to know anything else about the energy levels because it's really telling us the photon that's getting released. So remember that for an atom, put our atom up here. If this is the nucleus, right? This is n equals 1, n equals 2. Your higher energy level is in your higher n value. And so when our electron falls down, that process has to release some amount of energy, and that energy is going to be released from a photon. So because they've told us the energy of this photon or the wavelength of this photon, we don't need to worry about what the n values are. We don't have to calculate the energy that way because we already know what that difference is. So the energy of our photon is kind of equal to this change in the energy that the electron's feeling. So go ahead and take your E equals HV and C equals V lambda. And I want you to combine those equations so that way we can get an E of a photon and how it's related to our wavelength. So we want to combine these two things and then we'll move on from there. Now, if you've forgotten, c is the speed of light. V is our frequency. And this lambda is our wavelength. So we can solve for our wavelength as being the speed of light divided by our frequency. We can plug that in where we get h. Oh, sorry, we're not trying to solve for our wavelength, we're trying to solve for our frequency. So now we can replace our frequency with c over lambda, and now we can tie in the energy of the photon directly to our wavelength. Now, what does this h value, or this one, what does this variable stand for the h?
Planck's constant.
Planck's constant. And that's the one that's 6.626 times 10 to the negative 34 joule seconds. So we want to find that energy of that photon. So go ahead and plug in. So we get energy of our photon is 6.626 times 10 to the negative 34 joule seconds. Our C value is on your equation sheet as well, 998 times 10 to the 8 meters per second. And then we have 558 nanometers for our wavelength. So is there anything that we need to change about this before we plug it into our calculator?
Convert it into meters.
We need to convert the wavelength into meters. So a nanometer is how many, is it bigger or smaller than a meter?
Smaller.
Smaller. So our number down here should be getting smaller when we convert it into meters. So it should be times 10 to the minus 9 meters. And so what energy did you guys find for your photon?
You got 3.56 times 10 to the negative 19 joules.
All right. Did anyone else get 3.56? All right. And that's also what I got.
Professor, I had a
Actually, I
question.
got 3.57. Mm-hmm.
Why do we use the symbol V for frequency, not F?
Instead of F?
Yeah.
There's not really a great reason about why some of the symbols are the way that they've been selected, because it's not really V, it's supposed to be the italicized V, which is supposed to be how you can tell frequency instead of velocity. The shorthand is that I don't really know why we use it. I do know that F is sometimes used for Faraday's constant, but then the little f is used for, I can't remember off the top of my head. A lot of these come from physics on this side of things. So I don't know why it's that way. It's just been that way. Okay.
Yeah, because c is a velocity in this case, so that was kind of confusing me.
Yeah, and that's the problem with it, is that they use those different variables, and so it just really depends on that's the standard that they settled on. The harder part is that when you see it written out like on the computer, it's easier to tell italics versus regular, and so that's the challenge of it. Yeah. What I would recommend is look at the units for your constants, and sometimes that gives you an idea about what practical thing it would be tied to.
Right.
Like c is a velocity because it's a distance over a time. Yeah. Otherwise, not really a great reason. At least not one that I know. I'm sure there's probably a reason somewhere. All right. So we're going to look at number 7 as well. And so 7 is looking a little bit about our ozone production. Yeah. And so we have so much ozone that's already in the stratosphere. And then we're having it fall 3.2%. What it's trying to calculate is the number of kilograms of ozone that would have to be manufactured on a daily basis, so that way we can restore it back to its original level. From there, we want to look at, well, how much energy would that be? And then we have a reaction down here. And so we'd have to figure out how much energy that's going to require for us to do that part as well. So we're going to start with the first part. Let's figure out how much ozone we need to make first. And then we'll look at the second part, which is how much energy do we need for it. All right. So you can imagine that if this was our ozone amount to begin with, it's dropped down by 3.2%. And so what we want to do is we want to restore that. So our initial amount was 3.2 times 10 to the 12 kilograms. And so we want to figure out how much has left. So we can go ahead and multiply that by 0.032, which is our 3.2%. And that's how much we need to recover. So total, that's how many kilograms we need to recover. Now, do we need to recover all of this in one day, or how many days does it give us?
100 days.
Is it just 100 days?
100 years?
It's
Oh,
100 years. So we need to figure out how many kilograms per day we need, but we have 100 years to do this. So this is our total amount. So now we're going to break that down. We know that we have 100 years to do it. We know that 1 year is 365.25 days. Eventually those leap years will add up for us. So we divide that by 100, divide that by 365.25. And so we're making roughly 2.8 million kilograms per day. Does anyone have any questions about that? Okay, so now it wants us to convert that over into energy. So the thing that we need to figure out for energy is that we know that we're making this from this equation here. So if we want to figure out how much energy, what would be another term that we could look for? What would we need to find for this reaction to answer our energy question?
Is it a photon on either side, one of the sides?
So we could think about the photon. The challenge with the photon is then we would need to know the energy required to break our bonds and form our new bonds for each of those photons. And so that is one way to approach it, but it will be actually a challenging way to do it because we would have to break apart all of these different bonds with our different photons. Is there another way that we have like a standard set of information where if we wanted to figure out the total energy that's either released or required for this reaction, is there another way we could do that?
So I thought you would be given the enthalpy for this problem or this section of the problem. That's why.
So on a quiz or exam, I would have to give you the enthalpy for it because you guys don't have the ability to find it, right?
Mhm.
Your book assumes that you guys have your access to your book, which is why they don't just always give it to you.
Right.
So if we wanted to find the delta H of this reaction, how could we find it just knowing these pieces? We're going to look things up in the book, but what enthalpies do we need to look up?
The energy it takes to break a bond between oxygen.
So you can do it from your average bond enthalpies, or you can
Oh.
actually just do it from your heats of formation. So if we just wanted to find our heats of formation, is it products minus reactants or reactants minus products?
Products minus reactant.
Products minus reactants. So this is going to be our O3 minus that of our O2. You could do it by looking at your bonds, that this is a double bond with oxygen, and then that this one forms a double bond and a single bond. And so we have on average, we're going to break apart, let's see, 2 O double bonds plus 1, no, 2 single bonds.
So this is like CHEM 120 stuff.
Exactly. So we would have to look at finding your average bond enthalpies of changing one double bond of oxygen and producing two of the single bonds, and then we could look at that difference if you wanted to do it from your average bond enthalpies. But it's actually, I find it faster to just use our standard heats of formations. But both of those would work, right? Both of those will get us to our delta H. But you're right, on the exam or a quiz, I would have to give you one of these because you can't look them up, right? Now, when we're looking for our heats of formation, what should it be for our O2 gas? Do we even need to look that one up?
0.
It should be 0 because it's in its elemental form. And then for our ozone, I wrote this down. Ozone is 142.2 kilojoules per mole. So for this reaction, we would go through and we would have, for 2 moles of it, it would be 284. Per mole of our reaction. So right now, if we want to figure out how much heat we require, we know that we have 200 or 2.8 million kilograms of this a day. We can turn that into our grams. And then how do we get our ozone into a mass or into moles? What do we need to get our ozone into moles?
Molar mass.
How do we go from a mass to a moles?
Someone said molar mass.
Oh, perfect. Molar mass. I need to get this back up. Perfect. So we have 48.00 grams per 1 mole. And then we know that there's 284.4 kilojoules of energy for every 2 moles of ozone we make from our equation. And now I realize that I made a mistake. When I plugged in my value, this is going to give us how many kilojoules we need per day. So this is giving us
Oh, okay.
8.30 times 10 to 1, 2, 3, 4, 5, 6 times 10 to the 9. But did it want it per day for this question?
Total.
It wanted it total. So instead of using 2.8 million, what should I have used instead?
3.2.
Not the 3.2 because that is
Or the 1 point.
Would it be the 1 point?
It should be the 1 point. Very good. Because it's not that we have to remake all of the entire ozone, but we do need to make that difference. So it should be the 1.024 times 10 to the 11. And so what should we get down here on this side instead? And then once you guys finish that, let's see how you feel about this one before we move on.
Is it 3.03 times 10 to the 14?
This one is I managed to erase it from my calculator. Let me see. Yes, 3.03 times 10 to the 14. Very good. So the thing about chapter 20 is it's really about, it's not about necessarily covering new material, it's just about applying things that you already know. And so it's in some ways like a refresher of different topics. A lot of it is kind of like Chem 120 stuff, us pulling things from back there, stoichiometry, things like that. And then it's just giving us some context of it, right? So the big part to take away from this chapter, it's not just to memorize over and over all the different like nitrogen cycle, oxygen cycle, carbon cycle, but it's more about making sure that you remember how to apply some of these different concepts into some context, right? And so that's where we're kind of looking at. The other part is the big one is photochemistry, because we haven't really discussed it in many other ways. So remembering what the difference is between photodissociation versus photoionization, and then how you find the energy of photons and what that's related to in that process, right? So that's kind of what you're looking at from this chapter. Okay. Good. So it seems like some of us still a little bit unsure, right? So if you want a clarification on any of this part of the question, you can always ask me, or you can put it into the chat, or you can send me a chat. But it's hard for me to clarify things for you to make you feel more confident with the question or with the problem if you don't ask what kind of part we're struggling a little bit on.
Professor,
Mm-hmm.
I had a question. So for my homework problem, this is 3.5%. I'm not sure if it's different for yours, but I got a different value for the.
So you should get different ones.
Okay.
Different. So when we look at the question, let's see, this is. So this question is what they call an algorithmic one. And so they change this value each time.
Oh.
So different people will get different ones. So like now it's 9%, right? And so then you would just have to redo it. So the numbers do change. It's just the process stays the same.
Okay.
Mm-hmm. Good question. The next one that we want to look at is we're going to look at number 10. Now, I think that this should be a very straightforward question, right? It gives us the decomposition reaction to make concrete or quicklime. And so we shouldn't have too much of a problem going through on this one. It gives us the mass. And so we just want to make sure that we know how to go from one to the other. Now, the part that I liked about this was that I think sometimes we forget about how much CO2 gets released through other industrial processes besides just making energy, right? So this is just what they do in order to make cement or steel making to make this calcium oxide. But the overall chemistry of it, the calculation should be fairly straightforward for us. So if we're starting off with the mass of our CO2, or sorry, not that, the mass of our calcium oxide, how can we get that into a mass of CO2? What do we need to do to that calcium oxide?
Is it the mole ratio?
Right? So we are going to use the mole-to-mole ratio, right, of calcium oxide to moles of CO2.
But before
But
that,
how do we get from the mass to the moles?
the molar mass of calcium oxide?
So we're going to use our molar mass, and then we'll use the mole-to-mole ratio here. So these are our coefficients. And then this should be our molar mass to get it back out into kilograms of CO2. Well, I guess we have to change it from grams to kilograms. So I'll let you guys get started on that one. Do you guys need me to break that down further, or do you guys feel comfortable moving forward with that one? When you get your answer, go ahead and put it in the chat. Good. So what value did you guys get for this one?
I got 7.8 times 10 to the 9.
10.8 times 10 to the 9 kilograms. And that is also what I got as well. And so when we talk about like some of what this chapter is about green chemistry. And some of what we're looking for is we're trying to take this, look for alternative pathways to do certain things, right? And so one of those things is that even if we reduce all of our energy production to renewables, right? If we don't find alternative pathways to making something like this calcium oxide, if we always rely on this process of just decomposing the limestone, we're still going to be releasing this tremendous amount of CO2 every year as well, right? And so there's different ways for us to approach that carbon dioxide mitigation. Some of it is just by us finding a new pathway. So instead of doing this same thing over and over again, where we're taking calcium carbonate and just heating it up, if we find new chemistry for this, then we can reduce all of those CO2 emissions as well. Right? So I think that part's kind of interesting about green chemistry. The next one that we're going to look at is we're going to look at question number 12. Now, this one's a little bit tricky because it has us going back to something we haven't talked about for quite a while, which is our half-life reactions. So you want to look at your kinetics. And if you go back to your kinetics part, we should have a half-life for our different order reactions. So it tells us that we should assume that this is an elementary reaction. And it says a sample of air at a certain temperature is contaminated with 2.0 ppm of nitrogen monoxide by volume. Under these conditions, the half-life of the reaction has been estimated to be 6.4 times 10 to the 3 minutes. And so it wants to know what would the half-life be if the initial concentration was 13.5. So we're going to change that concentration, and then we need to find a new half-life for it. Now, when we're looking at this one, I want you to take a moment, and I want you to figure out what order is this reaction. So it's giving us this big clue that it's an elementary reaction. So we know that our rate should be K of our NO squared and our O2. And so if we saw just this, what kind of rate or what kind of reaction order should this be?
Third order.
Third order. And so that becomes a challenge, because do we have a way to solve a third order half-life equation?
No.
No. All right. And so this is the tricky part about it, which is why I wanted us to talk about this question, which is why we're all here. Right? Because sometimes we have to think about the bigger picture. So when we're looking at this nitrogen monoxide, right, and it has a concentration, does this O2 concentration, is it ever really going to change that much in comparison to our nitrogen monoxide?
No, it's in excess.
No, it's a huge amount. So this oxygen is so large that even as we go through this process, that concentration is not really going to change. And we can see that because of the 2.0 ppm, right? So the 2.0 ppm is a very small amount compared to how much O2 we would have present. So that means that we can kind of get rid of this O2 because it's going to be a constant. We can incorporate it into our K because it's not going to change. In the same way that you would do it with a solid or a liquid. Now, I wouldn't have given you something quite as tricky without like more hints in there for your quiz or your exam, but I just want you to understand how they came up with that conclusion. It's because your oxygen is so much larger. Right? When you do atmospheric chemistry, the other one to watch out for is your nitrogen amounts, right? Because nitrogen gas is something like 70 to 80% of the atmosphere, depending on if it's got water in it or not. And so a lot of times our nitrogen concentration is also going to be pretty much constant compared to the other one because it's so very, very large. So this is our second order reaction. The first thing that it wants us to know is it wants us to find a half-life. So we should have a half-life equation. And what equation would that one be for our second order?
The ln of 2 over, or the 1 over the constant K, the concentration of like the initial concentration.
In the initial concentration, right? Yeah. Very good. Now, do we know this K value yet? Is it something that's given?
No.
No. So we're going to first find the K term. Well, so there's kind of two ways to do it. One is we can plug in for our initial part. So we can do our half-life as being 6.4 times 10 to the 3 minutes is equal to 1 over K. And we can put in our 2.0 ppm. Now, does anyone remember what ppm stands for?
Parts per million.
Parts per million. Now, is that a type of concentration?
Yeah.
Yeah, it is, right? Because it's an amount of material over some size, so it's a quantity. So it is a pp, it is a concentration, so we can use it in here. So we can do this to solve for our K, and then we can plug in our new A naught to do that. You could also have set it up as a ratio for our first equation to the ratio of our second set of conditions is going to be equal to A naught for our second over A naught to our first. And so that kind of means that the more material that we have to start with, the faster our rate should go, right? And so we can kind of connect those two values. Basically, we solved this K for that. And so this would be we would have two of these expressions because our K value is going to stay the same. We would have one for the first set of conditions, and we'd have a second one for the second set of conditions. Because we can set them both equal to the same value of K. And so when we rearrange those, that's how we get this equation down here. So both of them work. I prefer this method where I just plug one in and I go through that other one. So that way I don't have to worry about rearranging them, because if you notice that these two end up being reciprocals of each other, right? So it's not always 1/2. You have to pay attention to that side, right? But either one of those works. So if we solve for our K, we get that value. And so if we want to find that new half-life, we just plug in our 13.5 ppm for that K. And we get 948 minutes. And I guess in this case, we only have 2 sig figs, so they want 950 minutes. Does that kind of make sense? I know there's a lot of variables going on. Is there any part that you guys want me to clarify on that one?
So I don't have the question pulled up, but they gave you the initial half-life. That's
So they gave us the initial half-life. So they gave us that for 2 ppm, we had this half-life of 6.43 or 6.4 times 10 to the 5.
Cool, thanks.
Yeah, so they have to give us at least one of them, because one equation can only solve for one unknown.
Right, you need to find that K.
Mm-hmm. So one of the tricky parts about ppm is most commonly used for how much of a solid you dissolve in a liquid, right? And so they normally make it as a mass per volume, and they use a density to do that conversion. But it can really be anything in relation to each other, right? So when it's saying parts per million, it could be saying 1 milliliter inside of 1 kiloliter of stuff, or 1 milliliter inside of 1,000,000 milliliters. All of that is equal to a ppm. We see it often because they do 1 milligram per 1, not meter, 1 over 1,000 liters, or you see it as 1 microgram per liter, because they're using the fact that most of those solutions are going to be in water with a density of 1 gram per 1 milliliter. So they kind of get mixed around in there. It is most commonly done for solids inside of liquids, but it can really be for anything. We see it in air as well, because they can compare our masses of our air versus your total volume of it. So you can do it mass to mass, you can do it liters to liter, volume to volume, you can do it mass to volume. You're just making that assumption that your density is about the 1 to 1. Any questions on that part? Then we're going to look at question number 13. Pull that up. And so this one is pulling us back into our first order kinetics. Right? And so it says the gas phase decomposition of peroxoacetyl nitrate, PAN, obeys first order kinetics. So it gives us a rate constant, and it wants us to calculate the rate of decomposition in molarity per second if the concentration is 0.35 ppm by volume. So there's that ppm again, but this time we're talking about volume. So it's probably going to be milliliters and 1,000 liters, something along those lines. And it tells us to assume STP condition. So that's a lot of information there. Let's go ahead and track it out. So right now, what we know is that this is at STP. So what are the temperatures and pressures at STP?
25 degrees Celsius, right?
So for gases, it's gonna be at 0 degrees Celsius. It's 25 when we're talking about thermal chemistry. So that's your delta H's, your delta G's. But for gases, STP is 0 degrees. So 273 Kelvin. And our pressure should be what?
1 atm.
1 atm. Okay, so that's what our STP is. And so they have us with a rate constant, right? So they're giving us a K. What we're going to try to do first is we want to find out how many moles of our PAN we have. So that way we can take our rate constant and we can compare it with a molarity. Because in order for us to solve our rate, we know that our rate is going to be K. And since this is a first order, we know that our rate should be our K times our concentration, our PAN. So we need this to be in moles per liter in order for us to use that inside of our K in order to get into molarity per second. So we have PV equals nRT. Let's take our ppm and let's turn it over into our volume, and then we can use that to find our N. So we can choose kind of any amount of volume that we want, right? We can choose in 1 liter, and then that's how we can figure out how much volume of PAN we have. We can do 1,000 liters, it doesn't really matter. Right? What we do know is that our ratio is going to be something of 0.35. So let's say that this is a liter, and this would be 1,000,000 liters. So
that's how ppm works. You just put whatever value you have
over 1 million of it. Yep. Because you're just comparing your ratio. So when they tell us that it's a ppm by volume, then it just means that, well, if we have 0.35 of them, then we had 1 million of the element. So it's always what you have over your total. And so it's just 1 million times bigger than whatever your value is. So if you were at 2 ppm, it would be 2.0 liters over 1 million.
Cool.
Yep. So for us, our units for molarity is moles per liter. And since I'm going to try to get into molarity anyways, I'm going to go ahead and I'm going to multiply this by 1 liter. That way, when we find this N, this is going to be our number of moles of pan in 1 liter of solution. And then we'll be able to plug it right into there. So our N of our pan is at a pressure of 1 atm. This is going to be 0.35. We have our R, 0.08206 liters atmosphere. Now, it's been a while. Make sure that you don't use the R, which is the 8.314, because that is going to give you joules, right? You want to make sure you're using the one in liters. And so this becomes 1.6 times 10 to the minus 8 moles per liter. So our rate has a K of 4.9 times 10 to the negative 4. Our concentration is 1 point, sorry, that shouldn't be. (1.6 times 10 to the negative 8). And that's our molarity. And so we should be able to use that to find our new rate. In molarity per second.
Professor,
Mm-hmm.
why did we use 0.35 liters over 100 liters for the volume?
Sorry, this isn't 100 liters, it's 10 to the 6.
Okay.
Yeah. Not a huge fan of writing on the tablet yet, but we're getting better at it, hopefully. So what rate did you guys get?
Professor,
Mm-hmm.
can you explain how you got the volume again?
Are you talking about the 1 liter or are you talking about the 1 million liters?
The 1 million.
All right. So it's telling us that we have a concentration of 0.35 ppm.
Okay.
So 0.35 parts per 1 million.
Oh, okay.
Okay. So that means that if we had it in terms of liters, that would be 0.35 liters per 1 million liters.
Oh, okay. Got
Okay.
it.
You can also do it as milliliters per milliliters, but since our unit has to be in liters anyways, then I might as well just use liters to begin with.
Yeah. Okay.
Yeah. So
Thank
it's that ppm term. I think it's the most commonly used concentration for like the health field, right? For a lot of like solutions you guys make it in like a hospital and things like that when you guys prepare drugs. But it is one of the most, I guess, the concentration where I see the most errors, right? Molarity is a lot easier for people to understand, and mass percent is easier, but ppm kind of throws us for a loop because it can be masses, it can be volumes, it can pretty much be anything.
Okay. Thank you.
So in this case, the concentration is equal to the moles because it's just moles over 1 liter, or is it moles over?
So we would still need molarity, right? So we would still need it to be moles per liter.
Right.
And so what I did was I just made sure to use 1 liter when I plugged it in. So that way we found the moles per liter.
Right.
Right? So if you have plugged in a different value, then you would just have to take your number of moles divided by the value you plugged in.
So is the rate 7.7 times 10 to the negative 12?
Yep, 7.7 times 10 to the negative 12. Very good.
Wouldn't the liters have to be on the bottom for it to be per liter?
So you do need your liters to be on the bottom for it to be per liter, right? Now, what I would say is that when we found our number of moles, what total volume were we looking at? Because we got our amount of pan in terms of a concentration. So we had to choose a volume that we were going to find the number of moles for. Okay. And so the volume that I chose was 1 liter. So inside of 1 liter, there was this number of moles. And so that's how it becomes per 1 liter, is because we used 1 liter up there.
Okay.
So in some ways, what's kind of going to happen is that these liters would cancel, our ATMs would cancel, our liters would cancel, our Ks cancel. And so we're going to find this in terms of mole. Right? So we find the number of moles. That number of moles came from 1 liter of sample.
Okay.
And so if we put them together, now we have the number of moles per liter, right? Because this was a conversion factor now. So it's one of those things where if you're mindful about your values that you choose, then it makes it an easy transition to molarity. Any other questions on that part? So we have 2 more to kind of go through. The next one is going to be number 16. All right, so number 16 is a glass of water is at a pH of 7. And then we're exposing it to dry air. Right? And so it wants us to calculate the pH when equilibrium is reached between the atmospheric CO2 and CO2 dissolved in the water. And it gives us the constant, the Henry's law constant for CO2, which is 0.032 moles per liter atmosphere. So we need to find that new pH. Now, the reason why I chose this one is that this one's a little bit tricky. And that's because when we're looking at this, what we need to know is that when CO2 dissolves in water, it doesn't just sit there as a separate CO2 molecule. It kind of goes through a reaction where it becomes H2CO3. And so what is H2CO3?
Acid.
So it's an acid. This is carbonic acid. So it's a weak acid. And so that's why our pH is going to change, is that we have a weak acid that we're going to make. And so we're going to eventually deprotonate our weak acid. And so that's going to change things for us. So the first part that we're going to do is we're going to find out how much CO2 dissolved to begin with. And that's where Henry's law is going to, or Henry's law's constant is going to tell us. So Does anyone remember what Henry's law, what that constant means? So we have 0.032 moles per liter atmosphere. What does that tell us? Or what is that going to help us do? So Henry's law constant, right, is telling us kind of like our dissolution. So we're going to use that to figure out how much of this gets dissolved inside of our solution. So our amount of our CO2 for dry sea level and air, we would have to go back to that table and we would look it up. And so it's 0.033%. So that means that our mole fraction is really 0.00033 moles of CO2 inside of our entire fraction. So the pressure of CO2 that we see is that mole fraction times our total pressure. And what is our total pressure that we're exposing our sample to? So when we go back to the problem,
1 atmosphere.
1 atmosphere, right? So it says that we're going to expose this at 1 atmosphere. So that means that our pressure of our CO2 is this 0.00033 times 1 atmosphere, which is really like 0.00033 atmospheres of pressure. And so if we want to figure out how much dissolves of the CO2, we can take 0.032 moles per liter atmosphere. We can multiply it by our 0.00033 atmospheres. And we can get a concentration. So this is how much CO2, the partial pressure of the CO2 that's pushing out down on it. That's how much dissolves. And so we get something like 1.056 times 10 to the minus 5 moles of CO2 per liter of water. Or I guess solution would be a better term. So we have a concentration of our CO2. Does anyone have any questions on that part? So I'm going to make a new one over on this other side so we can kind of get a little bit more space. So we're going to take our carbonic acid and if we want to find its pH, then we have to do an ice table. So this would be our concentration. This is going to be 0 and 0. And so some of this is going to decompose, some of this is going to be produced, some of this is going to be produced. So do we know this initial concentration of our H2CO3? If we're assuming that all of our dissolved CO2 turned into H2CO3 when it went in there.
Mm-hmm.
We do, right? We just found that. And so what value should I be putting in for that?
The one you just got, 1.056.
times 10 to the minus 5, right? And so I can here update this one as well. Okay. So I have my equilibrium values. So what am I missing? What do I need to look up in order to kind of do this next part where I'm trying to find my x?
Okay.
I need to look for my Ka. So my Ka, I would have given this to you if this was a quiz in or exam, right? But for this one, we can find it as being 4.2 times 10 to the minus 7. So that means that 4.2 times 10 to the minus 7 equals H plus HCO3 minus H2CO3, which is the same as us saying x 1.056 10 to the minus 5 x. And so then we can solve for the quadratic.
We ignore it.
What was that?
Couldn't we neglect x?
So we're kind of close, right? This is 10 times 10 to the minus 5, and that's times 10 to the minus 7. So you could neglect x, but then you want to double check it, right? So if we do that, so 4.2 times 10 to the minus 7. So if we neglect x, we get something like 4.2 times 10 to the minus 7 times 1.056 times 10 to the minus 5 equals x squared. And we get an x value of 2.106 times 10 to the minus 6. And so when we check that, we get 20 or 19.9%. So can we ignore it?
Nope.
No, so we can't take the shortcut this time. So pay attention to your value of your Ka compared to your concentration. If we were at a much higher concentration, it would have been fine. But because our concentration of our CO2 is so low, then that's why we can't ignore it this time. So instead, if you go through the quadratic, you should get something like 1.9 times 10 to the minus 6. Is that what you guys got?
That's about right.
Okay. Now, can we stop there, or what do we need to do to that in order to finally finish this problem?
Negative log of it.
We gotta take the negative log. So we need pH of negative negative log 1.9 times 10 to the minus 6. And so what pH value did you guys end up with?
5.7.
5.7. In this case, I'm going to put 5.72 because remember that when you take logs, your significant figures are the ones after the decimal point. So we start off with 2 sig figs from our value, so we're trying to keep 2 digits after the decimal. So something like this question won't be on your exam number 2, but I will admit that I really like this one for when we have chapter 20 on our exam. Right? I like it because it had us combine a lot of different things that we've used. Right? We have to do things like, you have to understand the atmospheric chemistry side of things. We also go back to all of that equilibrium stuff that we worked on at the beginning of the semester. So this is something that if you're feeling a little bit unsure of, I would definitely recommend doing some more practice with them, right? Or asking questions about where you might have gotten lost a little bit along the way. I would give you some more guidance than this question by itself. Like I would have told you, you can assume that all of the CO2 dissolved would turn into your carbonic acid. But it does mean that you have to understand those processes put together. Now, exam number 2, I've put up your expectations for exam number 2 inside of today's lecture. So if you go to the module for today's lecture that says chapter 20 homework problems, you'll see the expectations for exam number 2. And so it should be chapters 15, 16, 17, and 18. So it doesn't include chapter 20 for next week's exam. Chapter 20 won't show up until exam number 3. Right? So you have some time, so you don't have to necessarily be an expert on it right away. But like the second half of this problem, where we had just the concentration of the carbonic acid and we wanted to find the pH, that's something that could be on exam number 2. And so we have
exam 3 going to be pretty soon since we pushed.
So right now, yes, I would say that there's kind of 2 ways that things are going to go. One is that exam 3 and exam 4 are going to get merged together and we'll just have one of those somewhere between those 2 things. But right now, I just have to wait until the district has to make their final announcement about what's going to happen. Because there's some variations where we might just come back for finals. We might do everything online. It's a little bit unclear. And so I'm just waiting for them to finalize everything so that way I can figure out whether or not we can even do the ACS exam or not.
So if we don't have the ACS, then you're just going to merge those 2 tests if it's online?
So if there is no ACS, then I will look at trying to merge exams 3 and 4. So that way we won't have quite so many exams. And then exam 4 would probably be, on that day, we would do like half of our final. And then the following day, we would do the rest of the final, something along those lines. So it's a little bit up in the air. Once they announce things, I'll revise the schedule. And then we'll talk about it probably next Monday. So I'm trying not to do like last time when the first part of this all started, where I told you guys a plan and then they changed it all on me. And then we had like a whole bunch of different plans. So once they finalize everything, then I'll let you guys know. But exam number 3 will definitely be on its way pretty close after exam number 2. So our last question that we're going to look at is question 17. And so this has to deal with radon. Right? And now the challenge with radon is that we haven't really covered nuclear chemistry yet. Right? That would matter if all of the questions on nuclear chemistry didn't really just have to deal with kinetics primarily, right? And so a lot of our half-life reactions we already know how to do because it's just about kinetics and rate. When we get into nuclear chemistry, then we talk about the mechanism that those things kind of go down by. But we should still be able to take care of these problems because even if we don't understand the way that things are decaying, we at least can figure out their rates because this one is going through a first order reaction. So right now, for all of your radioactive problems, unless it tells you, like it gave us the equation last time and told us it was an elementary one, and that's how we were able to figure out that it was a second order. If it's just a radioactive decay, you can assume that it's going to be a first order reaction. So for this question, what it's asking us to do is that it's giving us kind of like our basement room, right? And it's saying that this is 18 meters by 2 meters by 6 meters. Probably not those dimensions. It's probably only 2 meters tall, but it doesn't really matter. And so we're going to be able to use that to find some type of volume. And so what it's trying to have us do is calculate the number of our radon isotopes, or the number of particles at the beginning and at the end of 31 days, assuming a certain amount of partial pressure. It tells us that we're at STP again. So our temperature is going to be what if we're at STP? What should our temperature be?
273.15.
273.15 Kelvin. Our total pressure would be 1 ATM. But we don't necessarily have to know that, because we know that our partial pressure of our radon is 2.5 times 10 to the minus 6 millimeters of mercury. So what we want to do is we want to figure out how many liters total of sample we have. So we have a volume, and so if this is a box, we need to find the volume, or sorry, we have the measurement. So if we need to find the volume, it's length times width times height. So a volume becomes 18 meters times 2 meters times 6 meters. Now, is there a conversion factor that lets us go from cubic meters to liters? Does anyone happen to know that one?
Meters to liters cubed, right? Meters cubed.
So 1 cubic meter is 1,000 liters. 1 cubic centimeter is 1 milliliter. And so if you scale those up, then it becomes something like 100 times 100 times 100 is equal to 1 cubic meter, right? And so that's how you can figure out that ratio. But pretty much 1 cubic meter is 1,000 liters. So we can change that to 216,000 liters. Now, we can find out the moles of our radon or our gas because we have this ratio, right? We know that there's going to be the amount of air is our pressure of the air times the volume times R times T. And we can plug that in for 1.0 atmospheres. And then we can figure out what our total amount would be. Or since we're looking for our radon, we can look for the moles of radon. We can use our pressure, that 2.5 times 10 to the minus 6. We just need to change that into atmospheres. So we can update this one, 3.289 times 10 to the minus 9 atmospheres. Our volume is 216,000 liters. We know our R, 0.08206. And we have our temperature. And so let's see what we get. So as we start to fill those in, we should be able to figure out our number of moles. And the reason why we want to get to number of moles is at the end, what we're looking for is we're looking for our atoms. They want us to figure out how many atoms we have, because this is our initial condition. Would then be able to use our disintegration rate in order to, or sorry, our half-life to figure out a disintegration rate, and then we can figure out what we would have after at the end.
We got 3.17 times 10 to the negative 5 moles.
Very good. So we have 3.17 times 10 to the minus 5 moles. And so if we wanted that in atoms, we just multiply that by Avogadro's number. So this is our A naught. That's our initial. Because it's a first order reaction, what we want to do is we want to find our K. Now we know that T, the half-life, is ln2 over K. And we know that our half-life is 3.8 days. So our K value should be 0.693, the ln of 2. That's terrible. Oh, sorry. K. And this should be our 3.8 days. And we get 0.182 per day. Does anyone have any questions about where I got that part from? So the important part to remember is that for our radioactive one, we're a first order. So if we want to figure out AT, we have to figure out that the ln of AT is equal to negative K times their time plus the ln of A naught So we have ln of AT. This is negative 0.182. They said that we have 31 days. And then we had 1.9 times 10 to the 19 atoms of radon. So I'm just going to consolidate those a little bit. And so AT is equal to E to the 38.7489. I'm going to erase this box up here. We can write our answer up there. And so after 31 days, we should have 6.7 times 10 to the 16 radon atoms. We'll do more of these half-life ones when we get back into chapter 19, but this is something to touch back in on because it is just our kinetics, right? So it's all about a rate of things decaying. And so we just want to make sure that we remember our zero order, first order, and second orders, and then how we can use those equations to rearrange them. Does anyone have any questions on that? All right, so I think that should be it. I don't have any other questions to do from this homework one. If you have a question that you would like to see, you can always ask it in chat or you can hang around. We can do that. I'll give you guys a moment. I just want to check in, make sure that you guys got everything answered that you were looking for.